Okay, let's get started. So just a couple things. For your disclosure, this lecture is being recorded just because we would like to put up as much of the educational materials up on the web. We also find that a real valuable aspect to these lectures are also the question and answers. So first I want to encourage you to ask questions, and I'll be pausing at various points in the lecture to ask for questions. But at the same time, we have this microphone that we would like you to use, which has an on and off switch, so that we can capture the question accurately and the discussion that ensues. So, and Frank over there will be a faithful microphone carrier. So just raise your hand if you have a question, and we'll be happy to engage. So let's get started. So first, I just wanted to begin with an overall outline and teaching objectives for this first lecture. And we'll end with this slide to make sure that we address each of these issues, and if there are questions still remaining about understanding any of these teaching objectives, that'll be a good launch point for a discussion. So first thing I want to talk about is biological systems have a variety of spatial scales that we're interested in probing, all the way from the molecular scale to the organism scale. And so what I'm first going to talk about is the common approaches for modeling light propagation in cells and tissues, along with the applicability of these approaches and limitations across these spatial scales. And so once we have these models, we'll have some sort of predicted ability to model light propagation, but how we use those predictions are a bit different depending on whether your interest is concerning with therapy versus diagnostics. So there's a slightly different way that one has to manipulate the predictions that you obtain from these modeling approaches, depending on whether you're primarily interested in therapeutic application versus diagnostics. So we'll talk about that. Now, in the context of light transport, which is what we're going to focus on today, tomorrow we'll be talking more about wave propagation phenomenon, Maxwell's equations. But today we're going to talk about light transport. And within light transport, kind of the critical thing one has to understand is something called the radiance. It's kind of the fundamental metric by which all rigorous light propagation models in radio transport predict the radiance. And the radiance, once you have the radiance, you essentially have everything you want to know about the light field. It is, in general terms, a six-dimensional object. It describes the temporal, spatial, and directional characteristics of light transport, because in any system you have light that varies in space, in time, and then light can get to that location in a multiple of directions. And in the space that we live in, we just need to define two directions. So we've got one dimension of time, three dimensions of space, and two dimensions of directions. So we'll understand what the radiance is and how we can use the radiance to get the various metrics we want. In order to predict the radiance, one has to understand the fundamental processes with which light interacts with cells and tissues. And those fundamental processes, we're going to simplify them and just discuss primarily linear absorption and linear scattering. We'll first describe them separately, and then we'll combine them in a mathematical framework that will allow us to get what's called the RTE, or radiative transport equation. So we'll first understand how light propagation is modified separately by absorption and scattering processes, and how you can treat these simultaneously using the radiative transport equation. So these first kind of four teaching objectives are focused on mostly modeling and computation. And then we're going to switch gears a little bit and talk about the optical properties of tissue. And we'll talk about the origins for absorption and scattering in tissue, their characteristics, and their spectral dependence, and where these come from and what you have to be alert to. And these characteristics inform the details with how you implement any solution for radiative transport. And then finally, we'll find that the combination of these optical properties, together with the physics of light propagation, naturally give rise to characteristic spatial and temporal scales. And so we'll talk about those at the end. So hopefully we'll hit all of these elements, and of course, feel free to interrupt if you have any questions. So let's get started. Some of this will probably be reviewed for nearly all of you. Just want to remind you that light can be described or modeled in two ways. One, you can think of the kind of a classical wave description. Light is a transverse electromagnetic wave. It's transverse in the sense that the direction of propagation is mutually orthogonal to oscillations in both electric and magnetic fields. And we typically use this in biomedical optics. We're interested in kind of the typically a few hundred nanometers out to tens of microns wavelength range. You can also describe light in a particle or quantum description. These are kind of localized massless quanta of energy, which we call photons. And there's a direct relationship for the energy contained by a single photon, which is inversely proportional to its wavelength. So this is just Planck's constant times the frequency, which can also be described in terms of the wavelength, Planck's constant times the speed of light in vacuum divided by lambda, with Planck's constant here. And so we'll see that Maxwell's equations adopts this kind of classical wave description, which is very important for microscopy and any application which relies on interference. And much of our area in diffuse optics and particle transport, radiative transport, kind of relies on this underlying quantum description. So just to orient ourselves with respect to light compared to other forms of radiation, so we kind of are concerned with light from the ultraviolet to the infrared. Lower energy forms of radiation are microwaves and radio waves. Higher forms of energy are X-rays and gamma rays. So why this is important is that when you are perturbing or interrogating a biological tissue with ultraviolet, visible, and infrared light, what you're doing is that you are, primarily in the ultraviolet and visible, you're actually interacting with the electronic structure of the tissue. You're pushing electrons around, okay? And so by getting spectrally dependent measures of the light propagation, you actually are probing the electronic structure of your tissue. As you go into the far visible, into the infrared, you are stepping down in energy. Instead of probing the electronic structure, you're probing vibrational structures. Okay, so the absorption and scattering features are dictated by that level of structure and composition in tissues. And often the energy of photons can be described in terms of electron volts, and so 1 electron volt is roughly 1.6 times 10 to the minus 19 joules, and so that is sometimes a measure by which we describe the energy of a single photon. Okay, so this is kind of a review from high school physics. So with respect to biomedical photonics, we have very interesting spatial scales, right? On one end, we use microscopy to try to get both morphological and compositional information of cells and tissues. And, a basic cell type can have a spatial scale on the order of a few to 10 microns. And of course, the substructure within that cell has important elements down to tens of nanometers, okay? And I think one of our students talked about super resolution microscopy, the challenge of trying to use light to resolve structure and composition on spatial scales less than the wavelength of light, trying to push down to the hundreds and maybe even tens of nanometers. So this is kind of the micro scale of, I would say, biomedical photonics. And in this domain, to model the interaction of light with cellular and subcellular structures, you really have to take a rigorous Maxwell's equation approach, which I have here. Now, if you're interested in probing slightly larger spatial scales. You're not interested in, say, resolving a single cell or looking at the subcellular structure, but interested in how cells organize, how cells interact with their local structural matrix or their vasculature. You kind of get on spatial scales on the order of tens to hundreds of microns. And typically, because light is scattering, since the tissue is turbid, the optical phase relationships get randomized, and to the point where it actually makes better sense to set aside the details of diffraction and interference, but treat light as propagating as a photon, as a particle. And this gives rise to the radiative transport equation, the characteristic spatial scale in which you can transition from using a fully rigorous Maxwell's equation approach to a radiative transport equation approach is something called L sub s. This is referring to the single scattering length, the characteristic length in which photons encounter a scattering event in tissue. Depending on the tissue, this happens on the spatial scale of maybe tens of microns to hundreds of microns. This depends on the tissue. It depends on actually the wavelength as well. So, by the time you're at 100 to several hundred microns, it's safe to say, depending on the application, you could use the radiative transport equation and not worry so much about being faithful to a wave propagation approach. Now, as the light continues to propagate more and more deeply, and you're interested not really on the mesoscale of understanding the interaction between cells, matrix, and vasculature, but you're really interested in interrogating a whole tissue, looking at the vascular dynamics, looking at the organization of that tissue, you're really starting to look on the millimeter scale. And what happens is that the light has interacted with the tissue so much that it has lost all sense of its original propagating direction from its source. Light is almost traveling in all different directions perfectly randomly. And in that case, in many applications, it's sufficient to deal with light transport as a scalar field. So here in radiative transport, you still have to be very concerned about the directional characteristics of light transport. But if the light field if the light propagation has been fully randomized, you can actually make some pretty far-reaching assumptions and simplifications in that directional quality of the light transport and treat light transport as a scalar field, and this gives rise to the diffusion equation. Now, the spatial scale in which you can transition from a more detailed approach for light transport in the particle sense to this diffuse scalar field is given by L star, which is called the transport mean free path. And for tissues, this tends to occur on the order of millimeters. Okay, again, depending on the tissue and depending on the spectral regime. Okay, so I just want to talk a little bit more in detail about each of these three models. First, Maxwell's equations is kind of the gold standard for treating light propagation in any media. It's a rigorous model for electromagnetic wave propagation in turbid media. We're going to see this in detail in Janika's lecture tomorrow morning. It models all wave phenomenon, interference, diffraction, polarization, and it's accurate across all spatial scales. So if one had sufficient computational power and intelligence actually to solve this equation, you could ideally try and use this to solve problems across all spatial scales. The challenge is that the governing properties that you need to apply Maxwell's equation are two things called the dielectric permeability and the dielectric permittivity. And these values for these properties, they're highly spatially dependent because there's a lot of ultrastructure in cells and tissue. And in cells and tissue, the values of these properties are often unknown. So this is often difficult to apply directly. Moreover, the Maxwell's equations are very computationally expensive to solve, but it has been applied to small systems in microscopy. So there are a couple of groups, one Vadim Bachman's group in Northwestern, and we have scientists from that group, as well as Andy Dunn at UT Austin. They've pioneered the use of finite difference time domain and pseudospectral domain methods to apply Maxwell's equations to understanding how cells and multiple cells, cell groups, can modify light propagation in tissue. We're working on some modified techniques based on Huygens-Fresnel wavelets to solve Maxwell's equations, and you're going to hear that tomorrow. That has made some inroads in reducing the computational expense. But using Maxwell's equations to understand the interaction of light with tissue is absolutely essential on this micro scale. One can't take any shortcuts. Now moving forward, as I said, once you're on the domain of tens to hundreds of microns, we can kind of set aside aspects of diffraction and interference and treat light propagation as the transport of particles. And in fact, this radiate transport equation, which you're going to see a little later on in this lecture, can be derived from Maxwell's equations. But you have to make a few assumptions. First, you have to assume that each particle that creates the scattering lies in the far field of other particles. That is, a particle will be receiving a light wave, and you've got to make sure that that particle is receiving a light wave that is far enough from the other particles such that it's in the electromagnetic far field. And that there are also no correlations between particle positions, because if you maintain correlations between particle positions, then interference and diffraction can be propagated over large distances. And this kind of concept that you can start to transition from a ray propagation formalism to a particle-based formalism and ignore diffraction and interference breaks down if there's correlation in those particle locations. The things that you give up in radiative transport is that this is a scalar model that doesn't predict interference or diffraction, but you can actually write a vector-based equation in radiative transport that handles polarization. And so you handle polarization using a transport equation for each Stokes vector component. Stokes vector is a way it's an economical way of providing a complete description of the polarization state of light. And then let me just transition lastly to diffusion. So as I alluded to, radiative transport provides a solution, if you solve the radiative transport equation, for something called the radiance, which describes the spatial, temporal, and angular distribution of light in tissue. Now, if you're not interested, or the detailed angular distribution of light is no longer of concern because the light has been scattered so many times that the light field has been randomized in terms of direction, you can generate an approximate solution to the RT by expanding this angular distribution of light in terms of Legendre polynomials. And so this is sometimes called standard diffusion or PN equations, up to order n. Legendre polynomials are a subset of spherical harmonics. It assumes azimuthal symmetry. We'll talk about that a little later. But this approach provides a closed set of n plus 1 coupled PDEs. So if you go up to order 5 in your Legendre polynomials, you call the P5, you'll get 6 coupled PDEs, which can be solved nonetheless. Or what's most often done in our field is that we take the easy route and we just terminate this after 1. So we call the P1, or standard diffusion approximation, which is what's done. And this has a long history of development and usage in biophotonics and can be used very powerfully. A lot of the work in brain imaging, in breast cancer imaging, muscle physiology, early work in pulse oximetry was all done using the P1 approximation. So it can be very powerful. And they're highly accurate in systems which effectively randomize the light propagation direction, and this tends to be in highly scattering media and at locations that are far away from sources and boundaries, because if you have a laser source like this, all of the light is propagating in one direction. And basically, you're assuming in diffusion that it's basically the angular distribution is spherical, and this is basically a delta function. So when you're close to a source, this is going to break down. And also, when you have boundaries of refractive index mismatch, you have a very strongly angularly anisotropic distribution due to the Fresnel reflectance at that boundary. So let me pause there because I think we went through a lot of different concepts here. Are there any questions about these three models of light transport and when they can be applied or not applied?
So can you go back one slide?
Sure. Okay, let's get the microphone. We have a question.
So my question is, for this domain, the particle should be lying really far from each other. What is the distance?
What is the distance? Okay, so
we can consider.
So typically, what happens is this: is that in the radiative transport equation, there's a function called the phase function, which describes the angular distribution of light that is scattered by a particle. Now, what happens is that that phase function is actually dependent on distance from that particle. But once you get far enough away from that particle, that function doesn't change anymore. And that's the function that's used in the radiative transport equation. I think a rule of thumb, Jonica, please correct me if I'm wrong, but I think a rule of thumb is that roughly if you're 10 particle diameters away from the particle, you're in the far field of that particle. So basically, the particles have to be roughly 10 times their own size away from each other before you have to start to worry about interference effect and this simplification of using this far field phase function. Jerry, do you have anything to add to that? Or okay, good question. Any other questions? I'll just say one thing. Tissue can be viewed as an ensemble of discrete scatterers. You can think of describing tissue in a particle sense, that you have a tissue that has some background ether, and you have these particles of scatterers or absorbers. Or you can think of tissue as being a continuum with a continuous variation in refractive index, in which case one arises, well, is there any particle scattering happening at all? And so because when we say that light propagates from air into that window, we talk about refraction. We don't talk about scattering. And that's refraction due to a change in refractive index. One could say that there's actually no scattering in tissue. Everything is continuous refraction because you could imagine tissue as having a continuous variation in refractive index. But you have some places where there's sharp discontinuity. So you can take both approaches, right? And in kind of imagining or in your mind what's happening within tissue. Okay. Any other questions? Okay, we'll move forward. Okay. Okay, so the next thing is I wanted to talk a little bit about diagnostics versus therapy, and we had a couple of several nice presentations early on about people from Massimo and Circuit Core, and this is what they do. They shine light into your finger, and you see my whole finger glows, and there is light coming out the back of my finger, okay? And that's because, if I do that with green, you're not going to see much at all, right? There's nothing coming out here, although they're sending lots of green in, right? And we'll see later on why that's the case. But here's a depiction of a finger, and if you are interested in a therapeutic response, if you're interested in phototherapy, what you're interested in is understanding this internal light field. You want to know at any location in a finger or in a skin lesion or in a tumor, what is the amount of light that arrives at any single location in that tissue. And you want to know that because you're probably doing a photothermal therapy. You want to cause a temperature rise, and the amount of temperature you're going to generate is going to be dependent directly on the number of photons that arrive at any given location. Or you may be pursuing a photochemical therapy where you want to actually activate a photoactive compound, and that degree of activation is going to be dependent on the total number of photons. Or there are other cases that's not therapeutic, but fluorescence. If you're doing fluorescence imaging, you've got to make sure you understand how much light is arriving at a certain location to excite that fluorescent dye that leads to emission. Okay? So here we're interested in the internal light field. In diffuse optics, this can be described in terms of effluence rate. It's the total amount of light impinging at any one location, and this will have some sort of characteristic decay. You have some lateral spread due to scattering, so you get dispersion in the lateral direction as well as in Z, in the axial direction. And like I said, this is important for therapy in fluorescence. Now, and we're focusing on the light distribution within the tissue. Now, if you're interested in diagnostics, well, you don't have direct access to this, right? All you can do is you can look at the projection of this, right? You can look at the reflectance, the light field that comes back out at you, or if you're fortunate enough to work in a thin tissue system like a earlobe or a finger, you can look at the transmittance. Okay? And so here are reflectance and transmittance not as a function of the depth, but as a function of the lateral distance. We sometimes call this rho. And we sometimes refer to it as source-detector separation, right? Because we're sending, in this diagram, sending the light field in at rho equals 0, and we're measuring the light out at various distances from that source. So rho is sometimes the distance between where you put in the light and where the light comes out. And typically what we try to do, at least in this simple experiment, we do much fancier things, but what we try to do is that we try to infer from this spatial or spectral dependence of light at a given spatial location something about the tissue properties, okay, from that. Here, we're not, what we want from a radio transport model is not a prediction of the internal light field, but the amount of light that gets out from the tissue, that escapes through boundaries, okay? And so one has to manipulate the solutions from your modeling equations in a different way in order to extract this metric of interest. And you'll see the impact of this in just a moment, okay? So ultimately, these light fields are dictated by how photons interact with the tissue. How does the photon life within the tissue lead to, you send in a photon here, it takes a tortuous path. Some of the photons come out, and some of them stay inside, and some of them, give rise to other processes. So we just want to make sure we account for everything. So let's just take a simple case where we have a source of light, we'll call it I naught, that is obliquely incident on a tissue with discrete scatters, absorbers, and fluorophores. So one outcome of this is because the tissue has a different refractive index than the air, some of the photons don't even get in, right? Some of it gets reflected. We call those specular reflection, R sub S. Some of the photons are fortunate enough to get into the tissue. Some of them can ramble around, multiple scatters, and come back out. In our field, that's usually referred to as diffuse reflectance, although the light field or this photon may not be truly a diffuse photon, but essentially diffuse reflectance refers to any light that's reflected from the tissue surface that actually entered in the tissue, interacted with the tissue in some way, and came back out. Some photons run into an absorber, and their life ends there, giving a rise to temperature. Some can undergo multiple scattering and get transmitted out, and then some can give rise to fluorescence, which then emits light at a different wavelength. So here I'm just going to account for light at the same wavelength. So this global light balance, this incident light has to essentially be equal to the sum of all of these four quantities: the specular reflection, the diffuse reflectance, the absorption and the transmittance. Okay, so this is just conservation of energy. But you can see that the spatial and directional distributions of the light are affected by the amount of scattering and absorber in the tissue. So first we need to understand how that happens. And if you simulate multiple photons, you can just kind of think intuitively that some sort of light field like this is going to occur, right? You're going to have a dominant direction here. There's going to be some lateral spread. And if we're interested in a therapeutic response, we may be interested, say, what is the light field at this location? And at this location, just intuitively, you can think that, well, when we're close to the source, there's probably a lot of light coming out in this direction. There may be some light traveling backwards because there's probably some scattering to kick light back. But you have this non-uniform, directionally dependent distribution of light at that location. And of course, it's not only, this is just a 2D projection of that, right? It's actually in 3D. And to describe this full directional dependence, not just the total amount of light in that location, but the directional dependence of that light in that location is called the radiance. And it's denoted typically by the letter L. It's a function of position, so I have a bold R to represent a vector, a position vector. Omega, capital Omega, is a unit direction, and that requires the definition of two directions, as we'll discuss in just a moment. And then, of course, we could be using a time-varying source, right? And so this could be varying with time. This has units of power per unit cross-sectional area per unit steradian. Steradian is a unit of solid angle, and we'll talk about how we compute that in just a moment. But so this is watts, or you can think of those as photons per unit time. Okay, so that's how you have space, direction, and time. Okay. So in order to, kind of what we want to do is that we want to solve for this. We want to solve for this everywhere in the tissue. That would give you a complete description of the light field in that tissue. So in order to get there, we first need to simplify the problem and work up to it in steps. Let's first just revisit some simple elements of light transport. First, absorption. So let's just consider a light source. This L, this is a radiance. S is just a position vector. It's distance. Omega is direction. So let's consider light traveling in only this one direction, forward. Okay? Now, if you have a slab which contains only an absorber, some of that light is going to get absorbed, and you're going to get less light coming out at some differential distance, ds. It's all going to be traveling in that same direction, omega. So if you want to look at the variation of that light, how does L vary with S? Well, the absorber is going to extinguish the light, so we know that the light field L at S plus ds is going to be at most equal to, if not less than, the incident light. So you got a negative. And the amount of decrease is going to be proportional to some level of absorption in that cuvette. We're going to call that mu A. And then if you integrate this, you get kind of standard Beer's law. Okay, that you have an exponential decay of the radiance as a function of position and in that same direction, omega, with mu A, which we call the absorption coefficient. The absorption coefficient has units of inverse length. Basically tells you how many, for a unit length of travel of a photon, on average, how many absorption events would occur along that length. And as we know, absorbed photons, are terminated. They no longer propagate in the tissue. Okay? So absorption doesn't have the ability to randomize direction, and it is also agnostic in terms of direction. That is, an absorber has equal efficacy no matter what direction the photon approaches that absorber. Now, scattering is a little different picture. On some level, it's the same. Same as that if we consider light propagating in a certain direction, omega, and it gets scattered, it also is gone from that direction, omega, because you've changed the direction. So in some sense, you still get an exponential decay of light, of the radiance, due to scattering if we're considering a single direction. The problem is that now this light has populated or added to the radiance at other omegas, okay? And therefore, you still need to account for that light because the light is still propagating. Nevertheless, if you're considering only a single direction and this ds is very, very small, such that it's unlikely for the light to get scattered again and repropagate back into that original direction omega, you can describe the depletion of light due to scattering through another law. It's not standard Beer's law, but it's kind of like a Beer's law for scattering. And we use another coefficient called the single scattering coefficient, mu s. It also has units of inverse length. It is, again, for a given path length, how many scattering events would occur along that path. So if you have something like 10 inverse millimeters, it would say that, well, if the photon were to travel a millimeter, it would on average undergo 10 scattering events. So if you think of attenuation or depletion of light along this direction omega in a solution that has both absorption and scattering, you can imagine a total attenuation coefficient mu t. And mu t is just the sum of mu a and mu s. So if you had both some of that green stuff and some of this red stuff, and this is a very, very thin slab, the loss of light in direction omega would be due to L naught exponential minus mu t s. Okay? Okay, so very simple. Any questions about that? This should be reviewed to almost all of you. Okay. So now the question is, how can we put all of this together? And so this is where we go into the radiative transport equation. And so we'll go through this slowly. It's a long equation, but actually conceptually it's not too difficult to understand. So let me just orient you again. So L is our radiance. It is dependent on position, direction, and time. So the left-hand side of this equation just says, how much is the radiance changing? Okay? It can change locally at a location due to a time rate of change. V here is just the velocity of light in the medium. So this is the time rate of change. The other thing is that the radiance has a spatial variation, right? So if you go from one location S to location ds, you're going to have a spatial gradient in that radiance. And so this is the gradient in that radiance along the direction omega, because at any one time we're looking at one direction. So this is sometimes called the directional derivative. Okay, it is a gradient, but you're taking the projection of that gradient along the direction you're considering. So you can either change light as a function of time or as a function of space. So how can that light change? Well, you can lose light. We just found out that we can lose light due to absorption or scattering, right? So, and the amount of light you're going to lose is the sum of absorption and scattering, which is mu t. It's a loss. That's why you have a negative sign here. So this is a loss of this radiance at this location r in this direction omega due to absorption or scattering. Okay? Now, we learned that the absorbed photons go away, right? They're dead. Or they give rise to light at other wavelengths, but we're just looking at one wavelength here. But the scattered photons live on to another day, right? But they've just now propagated on another direction, which we're not considering at this moment. Now, the other thing is that you can gain light. You can gain light because there could be light coming in from other directions, omega prime, that at this location gets scattered into direction omega. And we have to account for those photons. And this is what this integral represents. So let me take you through this integral. So first, we got to say, okay, how much light exists at this location that are traveling in these other directions, omega prime? So this is just, what is the radiance at these other directions? Okay, so now we know the light at these other directions. How much of that light is likely to be scattered into the direction we're interested in? That's omega hat. So this is what I referred to earlier as the single scattering phase function. It is the probability that light at this location R is going to be scattered from this other direction, omega prime, into the direction we're considering, omega. Okay? So you take, and then we have to consider every single omega prime. So we have to integrate over all directions. And all possible directions are all directions on a unit sphere. And so that's what this 4 pi here represents. It's an integral over the unit sphere. And we're going to talk about this in more detail. I just want to give you the overview right now, how one actually does this integral. And this phase function is normalized. So the amount of light you're going to get scattered from other directions into the direction you're considering omega is going to depend on the local amount of scattering you have, and that's mu s. Okay? So the first term is loss due to absorption of scattering. You're losing light either through the extinction of the photon or the scattering of light into other directions, omega prime. You're gaining light because light from other directions, omega prime, gets scattered into the direction you're interested in. And then, of course, there could be sources of light, like this laser pointer, which is injecting photons at a specific location and at a specific direction, and it can be time modulated as well. So this is the radiative transport equation. It's just a balance equation. Unfortunately, it's challenging to solve mathematically because you have an integral here and you've got derivatives going on here. So it's what's known as an integral differential equation. And so there's a lot of work with many approaches to solve this equation. So let me pause here just to see if everybody is comfortable, at least, with this equation. We'll unpack this more as the lecture goes forward. Any questions? Yes, Ching. Let's get the microphone.
I have a question.
If the light is on, yeah.
I have a question about the fluorescence.
The fluorescence?
Yeah, is it included?
So this equation, okay, so the question was, she has a question about if fluorescence is included in this equation, and the answer is no. This is a equation for a single wavelength. Okay, so this is what's called I think in nuclear transfer they call a single energy equation, right? So you could write a variation of this equation. You can go into some nuclear textbooks or radiative or atmospheric physics textbooks that give you the wavelength variation. There's another thing called the spectral radiance where you actually have a lambda there, and so you want to look at this full spectral dependence. That adds a little bit of complexity there, but it is definitely tenable, and you can then use that spectrally dependent radiative transport equation and apply the same tricks for approximations that we're going to talk about later on. And I can give you some references for that. Yeah, so this is a single energy equation. Yeah. Any other questions? One more.
So this equation is only work for the standard diffusion, right?
No. This is not, we've made no assumptions here with respect to the angular distribution of light or to the values of absorption and scattering. Standard diffusion is an approximate solution to this equation that is only valid under a subset of conditions. So the only approximation we've made here is that we're assuming that we're not considering diffraction, we're not considering interference, we're assuming a random medium so that those interference effect cannot be propagated over long distances, and we assume that the scatters are each in the far field of each other.
Okay.
But so if you're willing to adopt those limitations in a particle description of light transport, this is a fully rigorous equation. Jerry, do you have something to say to amplify?
Comment that the normal usage of standard diffusion approximation is of the lowest order angular approximation to this equation, radiative transport. So you have a whole ladder of approximations depending on how many angular moments you include in the description of the solution. and the lowest of those is STA. Not, this is the highest of them. This has all the angular momenta in it.
Great. There's another one. Vikrant?
Just making sure this is also assuming that the tissue or whatever sample we're using is homogeneous, right?
Well,
Talk about
actually,
mutation.
one can write these equations with a directional dependence. I actually haven't written it here. You can actually write the mu t and the mu s as a function of r.
Okay.
And actually here in the phase function, I actually wrote it explicitly. You can write the phase function as a function of r. So if you admit a spatial variation of mu t and mu s, it's fine. You can use this for fully heterogeneous tissues. And, like Andreas Hilscher, who does a lot of tomography based on radiative transport, he does a full spatially resolved radiative transport equation. Yes.
Okay. Thank you.
Yeah, sure. Those are good questions. Any other questions or comments? Okay, great. Okay. So the other thing I just want to mention is that we can write a vector form of this equation to handle polarization. So I talked about earlier that, in fact, you can deal with polarization within the context of radiative transport, and that requires you to describe the radiance in a form that allows you to characterize the full polarization state of tissue, and that's called the Stokes vector. It has 4 components. You have basically dealing with the parallel and perpendicular components of polarization, and the stars just refer to the complex conjugate. And so you can write basically an identical equation, except you replace L with this vector I, and you replace the phase function with a scattering matrix, which tells you how polarization gets altered, how the polarization state of light gets altered upon scattering in the medium. Okay, and so this is, again, basically 4 phase functions here, pertaining to each of these 4 Stokes vector components. Okay, so there is some generality. So now I want to kind of go back a little and reconnect this concept. So let's pretend for a moment we can solve this equation, and we have L. Okay, we know this complete spatial angular distribution of light in our tissue. Now we need to use that solution to some application, and as I pointed out, how you use it may differ depending on whether you're interested in a therapeutic application or a diagnostic application. So let's think about this in the terms of a therapeutic application. You wanted to know the total amount of light in that tissue. We usually refer to this as the fluence rate. It is written as a lowercase phi. You notice phi is not directionally dependent. It's only a function of space and time. Because what you want is that you're at this location in the tissue, and you want to know what is all of the light emanating or impinging at that location. So you get that by integrating the radiance over the unit sphere, over all angles. You can, sometimes some terminology they call this S2, which is all that you have 2 dimensionalities in your directions. So let's just put up a diagram just to refresh ourselves on spherical coordinates. So x, y, and z are our Cartesian coordinates. In spherical coordinates, we have our 3 coordinates are r, the radial distance from the origin, theta, which is known as the polar angle. It is the angle off of the vertical component. So if theta is 0, you're kind of like looking directly upwards. If you're looking at theta as pi over 2, it's like you're looking at the horizon, right? And then if you're at theta of pi, you're looking directly downwards. Okay, so it's basically if you're looking up, horizon, downwards, so it's this. And then azimuth is for every theta, it's the revolution. So if I'm looking at the horizon, this is phi going around here. Okay, so we need to unpack this in terms of integrating this over theta and phi. And this is how it looks like. So if we depict a subsection of that unit sphere. So we're assuming that this is radius 1, and we look at the area that is circumscribed by a differential element in both theta and phi. The length of this edge is given by delta theta. It's just you're circumscribing an arc in theta. The length of these edges are dependent on theta, because if you're close to theta equals 0, you're not going to be subtending any sort of arc. It basically goes with sine theta, and it's sine theta times delta phi. This arc is going to depend in length depending on the element in phi. So this integral, essentially, the d omega becomes sine theta, delta phi. Your limits of integration are, as I said, for theta, looking upwards, you're at theta equals 0. Looking downwards, you're at theta equals pi. And for each theta, you go around the full phi, 0 to 2 pi. So this draws out the entire sphere. Okay? So if you have the full angular description of your radiance, this integral gives you the total amount of photons that are emanating from that location. And this is the fluence rate. Okay? And this, again, does not make any assumptions as far as the angular distribution. You presumably have a solution that tells you what is the amount of light emanating from this location for every theta phi pair. Okay? Now, assumptions are put onto that, say, in the standard diffusion approximation. Are there any questions about this? Fine? Okay. So now let's think about diagnostics, right? So diagnostics where we don't have access, or we're not interested in what's going on inside, we're interested in how much light gets out, okay? And so here, I'm going to look at reflectance. So here, I'm interested in this light field coming out. Of course, I've depicted z going downwards, which is a little confusing since my diagram here is z going upwards. But essentially, if you have a refractive index mismatch, if there's air here and there's the tissue here, then actually there's a discontinuity in the radiance profile in the tissue and outside the tissue because there's a Fresnel reflectance going on here. But essentially what we want to capture is all of the light emanating from the tissue at a location just above this the z equals 0 interface. So I call this the radiance at z equals 0 just in the negative z plane because I define z positive into the tissue. And we're only interested in all of the upward going directions. And the way that you can define that mathematically is that we're going to take this integral with respect to d omega, with respect to direction, and we want to consider only those directions where the direction we're considering, if you make a dot product with that, with the inward pointing unit normal, that dot product is negative, right? If the dot product is negative, then you know you're moving in the upward direction. And what we're going to measure in reflectance, so to speak, is going to be the projection of that radiance onto the outward pointing normal, the minus z direction. So this is essentially an integration of this entire angular profile in this upward hemisphere, and you have to project that onto the outward pointing normal. Okay? And so you can unpack that again in terms of theta and z. And that's what you have here. Okay. Any questions on that? Don't be shy. This is very confusing. At least I know I was confused when I first tried to understand this. Yes? Yeah.
So here we're trying to calculate what is the portion of light reflect from the sample. So we all know that when the light go into the sample, some of that gonna go inside and go out. How can we not take into account of the light that go inside and go out?
We do. So what I've done here is that in order to get this L of R at z equals 0 minus, you have to know the light that is on the other side, and then you apply something called the Fresnel reflectance relationship. So we're going to talk about that later. So I'm assuming that we know the L right on the other side of this tissue boundary, and that was determined based on the solution to the radiative transport equation, which gave us the solution right inside the tissue, and then we applied a boundary condition essentially to get that outward propagating light. So all I'm saying, so here I just wanted to show people, assuming we had the full solution, how do you use that solution to get what you're interested in? Because I talked about earlier how you have slightly different metrics whether you're doing diagnostics or therapeutics. So I haven't addressed how you get this, and we will. Yes, yeah. Okay. Other questions? Okay. So I think now we change gears because we're now moving. So we're going to set aside radiative transport for a while. You can, and we'll kind of now shift into kind of tissue optics. So we haven't really talked much about how the structure and composition of tissue informs all of this. So this is a fairly, I think, famous slide now in our field, composed by Steve Jacques, that really reminds us of the structural diversity of cells and tissues. What Professor Jacques is reminding us in this slide is that cells and tissues are remarkably heterogeneous with spatial variations that span multiple orders of magnitude. Okay, so in this case, he's depicting a mitochondria, which is a very important organelle within a cell. It's important for generating ATP, which is kind of the chemical fuel that cells live on, but it's also important in regulation of the cell cycle and other processes. But the mitochondria itself is on the order of a few microns. It should be micron, not millimeter. And so you can think in terms of light scattering that this whole ellipsoidal object scatters the light, and it does. But the internal organization and structure of the mitochondria is very complex, and with many, many membrane-bound structures. And these membranes have spatial scales on the order of tens of nanometers. Also, there's refractive index variation. So you have this tremendous diversity of spatial scales of refractive index variation that gives rise to light scattering. Of course, there are not only cells in tissues, there's also extracellular matrix. The cells reside within a structural context. The most predominant of which is collagen, and collagen itself has this tremendous ultrastructure down to the individual tropocollagen molecules have striations on the order of 70 nanometers, actually down to 60 nanometers depending on the tissue type. It's actually tightly regulated, these striations. Say in the cornea, it's very important for corneal transparency. But then these associate with each other and bundle with each other to give rise to spatial variations in refractive index on the micrometer regime in terms of collagen fiber bundles. Again, this should be micron, not millimeters, so this would be 2 to 3 microns. So we need to understand that we have spatial heterogeneities on spatial scales that are much smaller than the wavelength of light. So the wavelength of light we use is up here in the visible spectrum. So we've got lots of cellular and tissue ultrastructure that have characteristic length scales smaller than the wavelength of light. And then we have other structures that are comparable and larger than the wavelength of light. And from a certain standpoint, I'll show you that the characteristics of light scattering is quite different depending on whether you're dealing with a structure with characteristic spatial scale that's comparable or larger to the wavelength of light or smaller. Okay, and you can see this and other beautiful slides on that web link. So let's talk a little bit about optical scattering, and you'll see more of this tomorrow, but let's just remind each other. So in general, if you have an optical scatterer, it could be any shape, you have a plane wave that's incident on this scatterer. This plane wave will have some sort of polarization state. E stands for an electric field. This is the parallel component of that electric field. This is the incident electric field. This is the perpendicular component of that incident field. And it is incident on the scatterer, and there's a scattered wave that's generated because of that. So this is the parallel and perpendicular components of that scattered wave. It has some dependence on theta and phi. And to get from your incident to your scattered light, you have some propagation, because this will end up being a spherical wave. So you have an attenuation with distance. But then you have this thing called the scattering amplitude matrix. And this tells you how, say, an incident parallelly polarized wave can give rise to a scattered wave of the same parallel polarization or a perpendicular polarization. That's what these elements refer to in this top row. And then in the bottom row, you see how the scattering of the perpendicular polarization component can give rise to, again, a scattered wave with parallel and perpendicular polarization components. So this S is kind of a more refined version of the phase function that we talked about earlier, because it captures the impact of polarization, and it accounts for azimuthal and polar variations of that. And this scattering amplitude matrix can be determined through solution to the Maxwell's equation for this system. Okay? The reason why I want to talk about this is that once you solve that, you can define very useful metrics for light scattering. So let's just take a simple case where we have a plane wave traveling from left to right, impinging on a scatterer, and you have a detector that's directly opposite of the source. So if the scatterer weren't there, you would just measure I naught. Okay? Now in reality, you're going to measure something different than I naught, because the scatterer is going to perturb that plane wave. And most likely, the amount of light you're going to detect is going to be smaller, and it's due to the scattering of this wave. And so you can define what's called a scattering cross-section. The scattering cross-section tells you, well, let's remove this particle, and in its place put a black disk that absorbs all the light that hits it. And it asks, the scattering cross-section tells you what is the area of that disk necessary to produce the same reduction of light at that detector. Okay? So if this scatterer is not very powerful, so to speak, in scattering light, that scattering cross-section is going to be really small, right? Because you don't need a very large disk to extinguish the amount of light to create that drop in intensity. Okay? And so this scattering cross-section has units of area. It's sometimes expressed in terms of scattering efficiency times the actual area, cross-sectional area of the actual scatterer. Okay? So if the absorbing disk is smaller than the actual size of the scatterer, the scattering efficiency will be less than 1. It turns out that actually the maximum scattering efficiency that you can have is actually 2, and I won't get into the details of that. So some scatterers have effectively, if you had to replace them by an absorbing disk, the disk has to be double the size of the scatterer itself. And I can refer you to some electromagnetics text to talk about the details of that. But anyways, from this ratio of scattered to incident electric fields, you can extract out the scattering cross-section. And in terms of the scattering coefficient is related to the scattering cross-section through a number density. So if you know the scattering cross-section of a single particle, which you can calculate, you figure out how many of those particles do you have per unit volume. So this is a number per unit volume. This is a unit area, square meters or square millimeters. Then you get a mu-s that is in terms of inverse length. Okay? And that's, again, the inverse of that is the scattering mean free path. Okay. So mentioned or alluded to the fact here that there's a very different characteristic for light scattering for particles that are much smaller than the wavelength of light that we're using versus longer. So now I'm going to focus on that. This region here is typically referred to as Mie scattering. In fact, the Mie scattering solutions are actually global. They refer to this entire domain, but there's some simplifications that occur when the particles are much smaller than the wavelength of light, and that's really the Rayleigh limit of Mie scattering. That's called Rayleigh, sometimes referred to as Rayleigh scattering, but it's really the Rayleigh limit of Mie scattering. So I want to talk about Mie and Rayleigh scattering right now. So Mie scattering. So one thing I want to just emphasize here just physically, I should have made a slide, but Richard, can you turn on the light just real quickly? So Mie scattering is a situation where the particle is huge compared to the wavelength of light. So you've got this big particle. Okay, let's see if I can get something that's darker. Okay, that's not much darker. Okay. And you've got this wavelength which is smaller than that particle. Okay? And the reason why I want to make this point is that this light wave is shaking the electrons in that particle. Okay? So if you imagine that here, if you're generating dipoles all over the place. Here, the dipole may be facing up. Here, the dipole is facing down, right? I'm sorry, I should, right? Depending on the phase of that wave, right? And what we're doing here is that we're collecting the far field emission of that scattered wave. So you got these dipoles, they're all radiating from different locations in this particle, and you're measuring the scattered light, several classrooms away, okay? Now, because these are not oscillating in synchrony with each other, they're not because they're all at any one time experiencing a different oscillation, you're going to get a lot of constructive and destructive interference, okay? And that's why, now you can turn off the light, Richard, if you could. Thank you. So that's why this is the angular distribution of the scattered light from a water particle in the atmosphere 10 microns in diameter. Your wavelength of light is 650, it's red light. But you can see here, the particle is, more than 10 times, about 15 times bigger than the wavelength of light. And what do you see? So this is a polar plot. The light is moving from left to right. And you see all of this fine structure, okay? The other thing that you see is that most of the light is directed forward. So this is a logarithmic scale. So you see that there's the vast majority of light is scattered directly forward. Then you have, after this forward peak, you have a drop of 1, 2, maybe 3 orders of magnitude, and then you get all of this interference stuff. You have not as much light, maybe 1,000th of the forward-directed light scattered in all these other directions, but it's very, very structured. Okay? We call this highly forward scattering. This is a very asymmetric scattering profile. There are some analytic distributions, analytic expressions for expressing or calculating what's called the reduced scattering cross-section for Mie particles, and we'll talk about what reduced scattering cross-section is in just a moment. But it is, the key points here is that it's dependent on the relative refractive index of the particle to the surrounding medium. It's strongly dependent on the scatter radius, A. It's weakly dependent on the wavelength, so it drops with wavelength, but with not a strong dependence. And NP is the actual refractive index of the particle, M is the relative refractive index. And it's dependent on the cross-sectional area of the scatterer. And this is valid within a certain regime. But the dominant thing I want you to take away here is that Mie scattering, the angular distribution is highly forward-directed and displays fine structure due to this constructed destructive interference. Okay. Now this is very different than cases when the particle is much smaller than the wavelength of light. So when the particle is much smaller, the whole particle oscillates as a single dipole. So you don't get this fine structure because you don't get this interplay of constructive and destructive interference. It does depend on whether the light is oscillating, say, in the parallel polarization versus perpendicular polarization. And that's what I've shown here. When you have parallel polarized light, you have this lobe structure. Again, the light is propagating from left to right. If you have perpendicular polarization, it's completely isotropic, equal amounts of scattering in all directions. And if you have unpolarized light, you have this toroidal structure. The wavelength dependence and the size dependence is very different. Here, you get a dependence of the scattering cross-section with the inverse to the 4th power of wavelength. This is the classic explanation for why the sky is blue. You have much more strong scattering at the shorter wavelengths than at the larger wavelengths. You also have the 6th power dependence on the particle size. Okay, much more strongly depend on the size of the particle. And then this is the impact of the relative refractive index. But the bottom line here is that you're essentially scattering light pretty much uniformly in all directions. Again, this is a linear plot. This isn't a logarithmic plot. So the angular distribution is symmetric. You're also scattering equal amounts of light in the forward direction and in the backward direction. So people who are familiar with single scattering anisotropy, single scattering anisotropy or asymmetry of Mie scatters is 0. You have equal amounts of light scattered forward and backwards. And then, of course, the variation is very gentle. Okay, so that's fine. Those are nice textbook equations, but the reality is that tissue is populated with both Mie-type and Rayleigh-type scatterers. And so how do we deal with this, right? We don't have, tissue is not a monodispersed suspension of particles. So how do we deal with this? So we, especially in the diffuse optics literature, tend to simplify the scattering properties of tissue into 2 components. One is something called the reduced or isotropic scattering coefficient. It's termed mu sub s prime, and it's the product of 2 variables. One is the single scattering coefficient, and the other is 1 minus g. G is called the single scattering asymmetry or anisotropy, and it's characterized by the average cosine of the scattering angle. Okay? So let's think about this a little bit. So if something is highly forward scattered, then you're not deflecting, the angle of deflection is very small. So the cosine of 0 is 1, right? So if you're just deflecting slightly, G is going to be high. And in fact, for Mie scatters, the G tends to be around 0.9 or 0.95 or 0.99. Now, if we put in, say, 0.9, let's just put in 0.9 into this equation. You get 0.1 here, right? 1 minus 0.9 is 0.1, and essentially the single scattering coefficient gets multiplied by 0.1. You're knocking down that coefficient by 90%. Why can anybody, whereas in a Mie scatterer, G is 0. So mu s prime is equal to mu s. So why might you want to effectively reduce the scattering of a Mie scatterer but not reduce the scattering of a Rayleigh scatterer? Does anybody have any insight? This is a way to try to put scatterers of different single scattering anisotropy on equal footing, so to speak. So let's take a scatterer that has G equals 1. Okay? G equals 1 means that essentially there's no scattering, right? The light goes in and it goes out the same direction. So what we're interested in, especially in diffuse optics, is that we want to get an idea of how long the photon has to travel before the direction is completely randomized. So if G is high, okay, you may have scattered, but you didn't deflect the direction by very much, right? Because the average cosine is 0.9. So in order to randomize the propagation of the wave, you're going to have to undergo many more interactions with a Mie type of scatterer before the light field gets randomized than if you have a population of Rayleigh scatterers, right? So if you just compared the mu-s values, well, if I had 10 interactions with a mu scatterer and 10 interactions with a Rayleigh scatterer, you're going to have a much more randomized light field in the Rayleigh scattering situation than in the mu scattering. So what you need to do is that you need to basically do an effective isotropic scattering coefficient. And this basically tells you that, well, if I have a very high G, I'm going to have to undergo many more single scattering events in order to get an isotropic light field. Okay, so typically in diffuse optics, we really pay attention to this reduced scattering coefficient because it puts the scattering effectiveness of various particles on equal footing. Okay, any questions on that? And in reality, if you want a fuller description of light scattering, if you're really interested in understanding the light distribution, the angular distribution, there are other higher order moments to the phase function. So this is the first, what's called the first moment to this angular distribution of the light field. If you want to better characterize that light field beyond a pseudo-spherical or pseudo-isotropic, quasi-isotropic distribution, you have to consider higher order moments of that light field. And that gives rise to these P(n) approximations that we talked about earlier. But the P1 approximation, standard diffusion, just considers this first moment of angular distribution. So one of the take-home messages I spoke of is that for a me scatterer, you have a wavelength dependence which is 1 over lambda to the minus 0.37 in that one analytic expression. But in general, we allow that to be some sort of inverse power law. So what people do to extract a pseudo-analytic expression for the wavelength dependence of reduced scattering says that you have some baseline scattering at some reference wavelength lambda naught, and it varies to some minus b power. And some others say, well, in reality, you have two populations of scatterers. You have a fraction of scatterers that are Rayleigh scatterers, and the reduced scattering for the Rayleigh scatterers should go as lambda to the minus 4 power. And the rest of the scatterers are not Rayleigh scatterers, they're me scatterers, and you raise this to a power of b sub me. So you can use either of these. These are two very valuable graphs in a recent paper from Steve Jacques. You'll notice that b sub me, if you took the same data and you tried to fit it to both of these expressions, there would be a different extraction for the value of b than the value of b me. So the value of b me would be actually slightly larger than, slightly smaller than the value of b, because b has to account for both the Rayleigh and the me scatterers, and the Rayleigh dependence is to the minus 4 power. So these are circles for various tissues: skin, brain, breast, bone. The stuff that lies along this 45-degree line basically are tissues that don't have much Rayleigh scattering at all, because the value of b and b me are the same. These tissues that lie below that line have a significant amount of Rayleigh scattering, and that's why their value of b me is smaller than the value of b. Okay, and again, full details are in this. And then this tells you how this ratio between b me and b varies with the fraction of Rayleigh scatterers. Okay, here you have fraction. Okay, so this gives you an idea of, some tissues basically don't have a lot of Rayleigh scattering contributing to their optical properties. Others, you have to consider the Rayleigh scattering. The other thing is that different tissues have radically different values of A, which is kind of this magnitude of the scattering at a reference wavelength. And, epidermis and skin tend to be very strongly scattering. Things like breast and lung and other mucosal tissues tend to have much less scattering. Again, this is all from this reference here. The other thing to note is that this scattering anisotropy, this angular variation of light, is wavelength dependence. The angular dependence of scattering can be wavelength dependent, and these are for many sample tissues. Samer, question?
Yes, I have a question on the reduced scattering coefficient and how it relates to the radiative transport equation.
Yes.
So in the radiative transport equation, there are a lot of terms that dependent on angle. And in the reduced scattering coefficient, you're taking the average.
That's right.
So in that case, are you making an assumption that if you use the isotropic scattering coefficient that is the dependence on angle change somehow in the radiative transport equation?
Okay, so there are multiple questions to that question. So first, to solve the radiative transport equation, you need to have two things. You need to have the single scattering coefficient, and you have to have something called the phase function. The phase function is supposed to be, if you want to solve the system exactly, you need to have some knowledge as to the complete angular distribution of scattering for the particles in that system. So when you compute something like G, you are making an approximation. You would not be using mu s prime does not appear in the radiative transport equation. Okay? Mu s prime, you'll see later, appears in the diffusion equations. Because in the diffusion equation, you make a simplification for the type of phase function that you substitute into the radiative transport equation. Now, if you, again, terminate this angular expansion, I talked about expansion of this angular distribution in terms of Legendre polynomials. When you expand the Legendre polynomials, you're taking what's called moments of the phase function. You're trying to approximate the phase function by a sum of Legendre polynomials. And the first Legendre polynomial is just uniform. It's just a sphere. And the first term is a cosine term. So you get a slight forward bias, because cosine is positive in the forward direction, and then slight reduction in the negative direction. That's essentially the single scattering anisotropy. So when you terminate that spherical harmonic expansion at the first term, naturally what falls out is the first moment of the phase function, and the first moment of the phase function is G. Now if you expand to higher orders, you'll get, sometimes this is referred to as G with a subscript 1. It's the first moment. If you do the second term, the third term, you'll get the second moment, the third moment, the fourth moment. And that would give you, if you go to G infinity, you reconstruct the complete phase function. Did I answer your question?
Yeah.
Okay. Yeah, one more question.
Just to follow up to that question,
Yes.
so could you comment on the relevance of mu s and mu s prime in terms of the tissue geometry, or the three domains you talked about in the beginning, to say where mu s prime starts to become more relevant as compared to mu s?
Mu s prime on some level is always relevant. The question is whether it's complete or sufficient. In the diffuse domain, when light has completely randomized, mu s prime will give you a fairly good prediction. Using an analytic expression that's based on mu s prime will give you a fairly good prediction. It still has some deficiencies because even when you're using Legendre polynomials, you assume azimuthal symmetry. And so if you actually want to, even in the diffuse regime, fully characterize your light transport, you have to use actually full spherical harmonics, which has azimuthal dependence. But let's put that aside. Let's assume we don't have any azimuthal variation. Mu s prime, just characterizing the first moment is good when you're fully diffuse. Now, once you're in the mesoscale, or even on the order of a few millimeters, you have to consider higher order moments in the phase function. And there's been work from, Urbicio's group, de Persange's group in Lausanne, Fred Bevilacqua, that show Keenly's group that talk about how differences in the second moment and third moment of the phase function can impact diffuse reflectance and transmittance measurements, especially when you're in tissues that are superficial. So it's this, we sometimes call the diffuse regime, then we call the transport regime. And the transport regime, which is, maybe on the order of a couple millimeters or smaller, the higher order moments of the phase function become essential. And there have been work in our group and many other groups that give simple analytic approaches to doing that. And I'll actually be talking about one of those approaches on Wednesday.
Okay.
Yeah,
Thank you.
yeah. Jerry, do you have anything to amplify on those comments? Because I know you have...
I don't think so. I would just want to state that the scattering phase function in radiative transport unlocks the key to the behavior of light more than any other single quantity. And these issues of how many angular moments you need to describe the light faithfully is a key issue. It's all locked into that phase function. So these are terribly important fundamental considerations.
And the real challenge here is that in reality we have imperfect knowledge about the phase function in tissue. And what's typically done is that we replace this unknown phase function with a simplified phase function, which is called the Henry-Greenstein phase function, which has some really well-known deficiencies, but it has also, the simplicity also makes it powerful. And this is what I've shown here is the Henry-Greenstein phase function, which was first developed for atmospheric physics for various G's. And so this is, again, is on a logarithmic scale, and so you put in different G values, and you see how for G equals 0, you have this isotropic distribution, and it morphs to strongly forward directed light scattering. It doesn't have any of the interference, properties. It doesn't actually, tissues tend to have a tail that rises up in the backward direction. The Henry-Greenstein function is monotonic with angle, monotonically decreasing. So there are some problems with using Henry-Greenstein, which again could be rectified by using other phase functions. So we're almost done here. So just want to talk about, just like I did in scattering, we talked about the single scattering cross-section and how that gives rise to the scattering coefficient. For absorption, we have similar considerations. One thing you have to be aware of is that the metrics for absorption used by chemists is typically expressed differently than those of physicists. So chemists think about molecular absorbers, and they characterize the absorption by a molar extinction coefficient in units of per unit concentration molarity and per unit path length. Their chromophore concentration or their absorber concentration is given in units of molarity. You have a path length, and the product of the molar extinction coefficient times the concentration times the path length is commonly termed the optical density. So if you have an OD of 1, that means that 1/10 of your light has gone through. If you have an OD of 3, 1,000th of your light has gone through this cuvette. So they're doing everything in base 10. Physicists don't think in terms of molecular absorbers, but particulate absorbers. So you have an absorbing cross-section, just like similar to a scattering cross-section, and you have a number density. So here you have sigma A times the number density will give you mu sub A, which is the absorption coefficient. So again, it has units of length, because this is number per unit volume, absorption cross-section is unit area, you get mu A. So this is a depiction of absorption coefficient of important absorbers in tissue, going from the vacuum ultraviolet all the way into the far infrared. You see that in the vacuum ultraviolet out to around 200 nanometers. Water is actually a pretty important absorber. Water kind of disappears as a dominant absorber throughout the visible, and a little bit in the near infrared, but comes to be very dominant in the infrared. Collagen is also important in the infrared, but we're usually interested in the UV visible and near IR. Protein and DNA, which isn't shown here, have dominant, strong absorption in the ultraviolet. And then the dominant chromophores we tend to run into in tissue are hemoglobin. I've only shown 2 species of hemoglobin, oxygenated and deoxygenated hemoglobin. Melanin in skin is very important. Fat I haven't shown here. Fat, also lipids, have some absorption in the red. And one thing I want to emphasize is that this is on a logarithmic plot, and you see this dramatic reduction in the absorption of blood at around 600 to 650. In fact, the absorption of blood, depending on the species, drops by anywhere from 2 to 3 orders of magnitude in a very small spectral range. And this gives rise to what we know as the diagnostic or therapeutic window of light in tissue. Another way to see this graph, which I think is very interesting, is to take a ratio of the scattering to absorption. And that's what I've done here, is that for skin, I've said, okay, I know my scattering spectra for skin, and I can assume realistic values for water, for fat, for oxygen, deoxyhemoglobin, and protein, and I've plotted the reduced scattering coefficient over the absorption coefficient. And you see this diagnostic window very clearly. At around 600, you see this dramatic spike in this ratio, where you see that scattering is dominant over absorption. This enables very deep penetration of light, starting around 650 all the way out to about 1200. So this is kind of your diagnostic or therapeutic window. Below 600 and above 1200, you get increased absorption. In this case, it's due to hemoglobin, and then later on proteins. Here it's done due to water and lipid. So this also is important with respect to the application of various light transport models. If you're dealing with millimeter spatial scales and you're in this regime between, say, 650 and 1200, you can use probably the diffusion approximation, which we're going to talk about later on. But if you're outside that window, then you really need to deal with radiative transport equation, Monte Carlo, or even Maxwell's equations to get accurate predictions. And then finally, these absorption and scattering coefficient give rise to natural spatial and temporal scales. And so I've just laid out a few typical length scales for absorption. Absorption tends to be low in the red and near infrared, so these values are very large. They're on the order of 100 to 10,000 millimeters that light can propagate in tissue before undergoing an absorption event. Scattering happens fairly commonly. Single scattering events happen on the order of tens to hundreds of microns. And then you can combine the two to get a transport mean-free path. And then since you have the speed of light, this gives rise to temporal scales. And the reason why temporal scales are important is that there are a lot of techniques, such as time-resolved and temporal frequency domain techniques, that rely on modulating your light source in time to extract absorption and scattering properties, and it's the interaction of that temporal modulation with the time scales for absorption and scattering that give you sensitivity to absorption and scattering events in tissue. And here I've laid out important coefficients. We've seen mu sub t already. It's the sum of the absorption and scattering. We talked about the reduced scattering coefficient. You can then combine mu s prime with mu a to get what's called a reduced transport coefficient, mu t prime. We'll see mu effective on Wednesday. This is a natural length scale that comes out of the diffusion approximation. And then there are various dimensionless optical properties, the ratio of scattering to total attenuation called the albedo, and the ratio of reduced scattering to reduced transport coefficient called the reduced albedo. And these are prevalent in the literature and in equations where they non-dimensionalize the parameters. And so I'm just going to end here with the end of our teaching objectives. So hopefully we've started getting an understanding of light propagation across spatial scales. We need to use Maxwell's equations or radiative transport equations or simplification standard diffusion. Therapy versus diagnostic. In one case, we're primarily interested in fluence rate. The latter, we're primarily interested in transmittance or reflectance, and we talked about how you do the solid angle integration. We talked about absorption and scattering separately and talked about the radiative transport equation, talked about the radiance, optical properties of tissue. We know that now the origins and the characteristics and the spectral dependence of scattering, whether you have Rayleigh or mu scattering, or a composite of the two, and then we just ended with spatial and temporal scales. So before I turn it over to Dr. Spanier, who's going to speak to us about stochastic solvers for radio transport. I just wanted to open it up for questions in case anything percolated to your mind in the break. And if not, we can just move forward. Any questions? Yes.
So at the end, we talked about the... Thanks. So at the end, we talked about the Haney-Green phase function, right? Can you say a little bit more about what that looks like and what it does? It takes in G, right?
That's right. Haney-Greenstein phase function was a phase function developed for radio transport in interstellar atmospheres. And it has some nice properties that make it easy to deal with analytically. So first of all, G is the only parameter in that phase function. So once you define G, you get a curve for the, the probability of scattering as a function of polar angle. It is monotonically decreasing with angle, okay? And the nice thing about it is that since it is only characterized by a first moment, all the higher moments, second, third, fourth moments, are defined by that first moment. So the first moment is G. The second moment, G2, would be equal to G1 squared. Third moment is G1 cubed. So it's G to the nth power defines all of those higher order moments. Why that's important is that that governs kind of the angular spectral decay of the phase function. So there could be other highly forward peaked or phase functions that can decay more rapidly in the angular spectrum or persist longer in the angular spectrum. And so the Haney-Greenstein function is one. There are others called the Fokker-Planck phase functions. There are various types that have different higher order spectral behavior. Okay. But given this easy relationship for defining the higher order moments, it's mathematically a very interesting case as well as convenient case in some approximations. Other questions?
I have a question about the depolarization. What is the difference between when the light goes through the tissue and like how does depolarize in diffusion regime like versus like for example OCT or like single scattering thing? How does that depolarization? How much light go through the depolarization? Is that a way to calculate that or see that
So depolarization, I'll also refer over to Jerry because I know he does some specific work. Depolarization is actually a very complicated topic, and the amount of depolarization that occurs on a single scattering event depends on the characteristics of the scatterer itself. And so while there are lots of rules of thumb about how certain polarizations, persist for longer distances than others, and the conversion, really the only rigorous way you can handle this is within using the scattering amplitude matrix, which deals with how scattering, the two polarization components are altered by a scattering event and by persisting that through multiple scattering events. But I'll let Jerry fill that question out.
The polarization state of launched tissue is often thought of as imparting a memory to the photon. It remembers its origin and its direction, and it loses that memory as it scatters in the tissue. So, as Vasan said, the rate at which it loses that memory depends on the frequency of scattering and the tissue itself. And so what you really, there are rules of thumb, but you really need to sort of do the computation, iterate the scattering matrix enough time to see that you have a spherically more or less symmetric distribution of angles after a certain number of collisions. Yeah.
Other questions?
I have a question for the Rayleigh scattering, the plot. So how do you define the P and S polarization? That's
Okay.
like
Sure.
when you image a sample with a P.
Sure.
and,
P polarization is where the plane of the board is the electric field. So the electric field is oscillating in the plane of the screen. It's called transverse electric. It's also called parallel polarization. S polarization is perpendicular polarization. It comes from the German, I think, for perpendicular. There, the plane of the board is the oscillation in the magnetic field, and the electric field is oscillating perpendicular to the screen.
So it now means that your illumination light is P polarized or S polarized.
That's right.
It is.
That's right.
So when you illuminate with a P polarized, then with the light coming out from the particle, P polarized is plotted in that like red.
That's right. You have the lobed structure.
It's
Yes.
not like you detect it in a cross polarization.
No, no. You're just detecting the light. It's just yeah. That's right. Questions? Are we?
I have two questions. The first question is the Rayleigh scattering. Because I heard it before in the atmosphere. Rayleigh scattering, is that related? Or-
Yes. So I think the scatterers in the atmosphere tend to be much smaller than the wavelength of light, and so the reason why we see this blue background is that that's the dominant wavelength of light that our eye is sensitive to, that is being scattered by elements in the atmosphere, and you see it through the 1 over lambda to the 4th power. So it tells you that the smaller the value of lambda, the higher cross-section those particles, the scattering of those particles have, right? You know, the particles still do scatter in the red, but the dominant scattering happens in the blue. Yeah.
Another question is in the earlier slides, you have the energy conservation of I naught equal to RS plus RD plus A plus T.
Yes.
I'm just confused about the fluorescence. Is that in the equation or it's not?
So,
Is that-
So the absorption gives rise to a fluorescence photon. So I would say that the absorption happens first, and once it's absorbed, multiple things could happen, right? It could generate heat, or it can give rise to a fluorescent photon. But I would say that first the absorption occurs, and then I account for the entire absorption. The fluorescence, it's kind of not the direct topic here, but fluorescence usually happens at a longer wavelength. But if you want to do it slightly differently, you could say, well, the fluorescence plus the amount of heat generated would be equal to the amount of the absorption in that case, right? So I just use, maybe I should have used A with an arrow going to fluorescence, but the absorption event itself should account for the full energy of that photon. Okay? Yeah, fluorescence could be a process that results from the absorption of that photon. Okay, sorry, it's a little confusing.
So I have a very specific question. So in case that you work with tissue, we have a structure. How can you put that structure inside the equation? So, and how can you consider that tissue have a medium that have a refractive index fluctuation, and how can you put that into your equation? So I heard something like Wheaton-Martin family of autocorrelation, and my question is, where do you put that?
Okay, so So the question is that how can you model a system where there's, how do you put in tissue structure into your model? Is that what you're saying? Okay, so, and then you also talk about if you have structural correlation, how do you put that in? So that's a very complicated problem. So part of it depends on whether you want to model things within a wave context or in a particle context. If you have correlations, then it seems to me that it is the output that you're going to get you may be interested in interference or diffraction effects. So if that's the case, then you're going to have to use a Maxwell's equation type of formalism to model your system. And therefore, you would have to model, essentially define your electromagnetic properties as a function of space and then run your simulation. In the context of a diffusion or particle-based system, I'm less certain about how you can put in a factor that accounts for correlations, because in some sense the underlying ansatz for a radiator transport solution is that you're assuming there are no structural correlations. So I think I've seen people try to put in structure factors and things like that, but I'm not sure. It's probably a specialized sorts of equation. Jerry, do you have anything to add to that?
No, not really. I think, as Rosnan says, you have to take account of such correlations by looking at Maxwell's equations directly. And I think radiative transport is not designed to incorporate those kinds of effects. Polarization, yes, but not the others. Yeah. I also want to make a comment in response to the question about fluorescence. Of course, if you have fluorescent chromophores in the tissue and they give rise to new light sources in the tissue, they would generate random walks, particles that have to be followed in order to capture the full light field. So you can think of fluorescence as adding another set of transport equations coupled to the one you start with. The absorption in the first triggers a fluorescent effect, and the light moves with properties like the ones I'll be describing here.
So does that fluorescence get included in Q on the next slide there?
Well, again, the radiator transport equation that we wrote was a single energy radiator transport equation. So there would be another term in that equation similar to, but not the same as, the scattering term with the phase function. So in some sense, in the radiator transport equation, it's a really beautiful term. It's a term that tells you that you can have light from other directions that then contribute or populate the direction that you're considering. So in a similar way, you can have another integral, kind of like, well, plus some sort of density of fluorophores, integrating, it wouldn't be over all directions, over all other wavelengths you can have coming in that then undergoes some sort of wavelength or inelastic scattering or fluorescent process, all other wavelengths that can undergo a change in energy that can then populate the energy you're interested in. So you can have another term that kind of, instead of going from one angle to another, you can have a jumping term that goes from one wavelength to another due to an inelastic or a fluorescence, inelastic scattering or fluorescence event. Gotcha. So there are generalizations to this equation to account for that.
So would it be fair to say that this equation, since it only takes in term one frequency, that all absorption, and no matter what secondary phenomenon happens, whether it be fluorescence or fret, is all going to be deemed under absorption because it's either the heat or the fluorescence that happens?
Yeah,
in the
all
return to
we're
ground state?
doing here is modeling the light at that one wavelength. So regardless of whether fluorescence happens or fret happens or heat happens, it's irrelevant because the light at that wavelength is extinguished. Okay, so I think we should move forward and we'll have more time for discussion, but thank you. Very good questions.